The first one, we're going to look at an example. We're going to reference this later on as well. So we have the average wait time for 30 customers at 2 different restaurants. We have McDonald's and Wendy's. And I want to find the average wait time for each of these. So I want you to do it on your calculator. Focus today, we're going to be learning how to do a little bit more on the calculator. What I want you to do, if you go to your stat, edit, okay, first of all, if you have information here, just use your up arrow, get onto the title and push clear, enter. Remember, don't do delete. It takes out the whole list and it's kind of annoying to put it back in. So what I want you to do is enter all the McDonald's times in L1 and all the Wendy's times in L2. And I told you yesterday that you could do it on here, so now if we go to stat, calculate. Yesterday I had you go to one variable statistics, which we could still do it that way, but if we actually just go into 2 variable statistics, Mrs. Nealport is the nicest person ever, in case you don't know. All right, so if we want to just pull up both at one time, go into 2 variable statistics, your X list set as L1. If it's not that way, you just hit second and the number 1. Your Y list, go ahead and set that as L2. So check that those are the same. Then just go down to calculate, enter. Okay, so this is giving me a lot of information. And hopefully, if I typed in my data right, ours looks the same. So this tells me the mean for my X was my first list. So the X bar, the wait time at McDonald's, was 1.389 minutes. Then the wait time at Wendy's was set as my Y, and that's 1.391, or even you could say 0.7 if you wanted. So, just a fun way, that way you don't have to like enter one, clear it out, and then enter in the second. You can put them both in and look at them at the same time. And we have the mean for both times. So what do we see? They're very close. Is there much difference between 1.389 minutes and 1.39 minutes? No, so it's essentially the same wait time. So if you're trying to decide where to go when you're short on time, it looks like it really doesn't matter. It's about the same. If we had drawn a histogram for each of those, so if you look at your next slide, these are the histograms. What do you notice if you look at those histograms? Any thoughts? Do they look like it's the same wait time at both from this? No. McDonald's, it looks like either you're going to get served immediately or you're going to wait for a while. There's a lot of people that were down here even up to 5 minutes of waiting. Wendy's, you're probably not going to get served as soon as you walk in, but then it looks like you're pretty consistently going to get served somewhere between 30 seconds and 2 minutes in. But what's the longest you ever waited at Wendy's? 4 minutes, and that was only one person, a couple people that had to wait that long. So if you're looking at this, knowing that's the same average time, which one do you think you would pick? Wendy's. It looks like they are more consistent on being faster. Okay, McDonald's, it might be really fast, or it could be a long wait time. So this just kind of shows the mean doesn't tell us the whole picture. There's a little more to it. Do not delete this data out of your calculator. Okay, we're going to use that again in a minute, so you don't want to have to retype them all. Did you already delete it?
You put it in wrong the first time.
Okay. So, one way we could look at how spread out the data is something you've probably done before, the range. It's just your difference between the largest and smallest values. This is on your formula sheet that you get, just in case you ever forget. Third bullet down, range is largest data value minus smallest data value. So we can easily find that. So if I went to my example from yesterday with my 7 employees, my range is, what's my highest commute time? What's my smallest? So my range would be 38. You want to put a label, that was talking about minutes. Okay, so range is very basic calculation, just subtracting, kind of getting a feel for how spread out the points are. But there's a much better one, because the range doesn't show me, oh, is there just one person that had a long commute time or not? If I threw in that like 150 minute or whatever the number was yesterday, if I put in that commute time, what's going to happen to my range? It's going to jump up exponentially. And really, that doesn't give me the whole picture because it was just one value that was off. So the range, kind of like the mean, is not very resistant. It only really is a good idea for symmetric bell-shaped data. If your data is not, then it's not giving you all the information. So then we need what's called standard deviation. So this formula, it is slightly different depending if you're talking about the population or the sample. And kind of nice, if you forget what variables you're using, it's again on the formula sheet. When we're talking about the population, we use this little symbol, and that is called a sigma, just another Greek letter. And so there's a couple different ways of calculating it. Nasty looking formulas, but essentially what this means is you take each value minus the mean. So take my value, subtract the mean, square it. We'll do that for every point, add them all up, divide by, what do you think n is? The total number of points, and then square root the whole thing. This is another way of doing it, but I think if we have to do it by hand, the first one is a little bit faster. So if we're doing it by hand, I'll use this version of the formula. For a sample, it's essentially the same. The mean instead of mu would be x bar, but the difference is on the sample you would divide by n minus 1. So that is the only difference there. We use S for sample standard deviation, but again, if you ever forget, you have that formula sheet and it tells you what variables we're using. And so again, I like this version of the formula. This is a time-consuming calculation, so I'm going to show you how to do it by hand. I would expect you to be able to do it, so homework, test, quiz, I'll probably ask you to do one by hand, but then the majority of the time we're going to use the calculator to do this. So we're going to do some examples by hand with some smaller data sets, and then we'll look at how to do it on the calculator as well. So when we're doing this, we are going to make a table. So I told you have to take each value, subtract the mean, square them. We need our value. We need our value minus the mean. And we need our value minus the mean squared. So these are my x's. Can you guys look back in our notes from yesterday? What was the mean of this set when we did it yesterday? Anyone have that handy? I guess we could recalculate it too. Let's just round to 24.86. I do want to caution you, if you round too much on your mean, it will throw off your standard deviation. So you don't just want to round to like 24.9. Rounding in general is kind of bad. Throws things off. So then we do our value minus the mean. So 23 minus 24.86 is negative 1.86. And then what do we do to that? Square it. Okay, so next one I do 36 minus the mean, so minus 24.86. Square it. And I have 23 again, so same as my first one. If you want to kind of check yourself, add up all of your x minus mu's for me. So if you just add this column, what do we get? I got negative 0.02. Okay, if you are correct, this column should always add up to 0 because it's measuring your distance from the mean. Why did we not get 0 exactly? We rounded the mean. So it's slightly off, but it should be very close. So that's just an easy way, especially on a test, if you're trying to catch any mistakes, add that up and it should be 0, or if you rounded your mean, something very, very close to 0. All right, so now to get our standard deviation. Standard deviation is the square root of the sum of all of these. So now we add that final column. And we divide it by n, which is the number of points. We had 7 in this case. So we do the square root of 902.8572 divided by 7. So I get a standard deviation of 11.3569. We don't really have a good feel for what a standard deviation is yet, and we will talk about that a lot more later on. But right now, all I really want you to know is the bigger the standard deviation, the more spread out your data is. Okay, so if you're trying to compare two different sets, whichever one has a higher standard deviation is more spread out. The smaller the standard deviation, it just means all of your values are closer to one another. So let's say I wanted to find the standard deviation of a sample. Okay, so let's say out of that group I took a sample of 3 employees. If I want sample standard deviation, so sample standard deviation, it's very similar. We have to add up the values minus the mean divided by n minus 1. So if I'm going to do the sample standard deviation, I need the mean of this sample. Okay, so my mean, 5 plus 26 plus 36 divided by 3. So we have a mean of 22.3333. Let's just go 22.33 to kind of give us fewer decimals as we're working through that whole table. So we want to do standard deviation. We have to have our value minus the mean, and value minus the mean squared. So our values, we have 5, 26, and 36. So we take 5 minus 22.33 and then square. So if you were taking a test and you wanted to check yourself, what would you look at right now? If the middle column added up to 0, or very close to it because we rounded. So to actually compute our standard deviation, we add the last column. So we add those 3 numbers. But what do we divide by? Close. It's not, we have to do 3 minus 1 this time. Because this is a sample. So that's the only difference between the two. In a population, you divide by the number of points. In a sample, you have to subtract 1. So we have the square root of that number divided by 2. So we get a standard deviation of 15.8219. So how does that compare to our original? The original, when we did the whole population, the standard deviation was 11.3569. This is 15.8219. So this one's bigger, so what does that tell me? These points are more spread out than the original times. Okay. Let's talk about our standard deviation for that first example when we had McDonald's and Wendy's. So we kept it all in our calculator. So go back to your stat, calculate 2 variable statistics. So stat, calculate 2 variable statistics. So we get this thing. What things on here do you think stand for standard deviation? We have that S sub x, and the other one is sigma, depending on if we are talking about a sample or a population. So if we're talking about McDonald's and Wendy's, do you think 30 people, would that be a sample or the whole population? Sample. So we are looking at the S for each of these. So my McDonald's standard deviation versus my Wendy's standard deviation. How do they compare? Yeah. Wendy's is more consistent. It has a smaller standard deviation. Which is what we already saw on the histogram. Most of them were grouped closer together, so we knew they were going to be more consistent. Now we kind of have a number to justify that thought. So the smaller standard deviation, the more consistent they're going to be. I'm going to do one last example and then I'm done for today. So the last piece I want to talk about, variance, is one other measure of how spread out data is. And it's not hard to find if you have your standard deviation. It's just the standard deviation squared. And again, that's your next two bullets on your formula sheet. So population is sigma squared. Sample is S squared. So if I wanted to go back and find the variance of my 7 employees, if we go back and look at that slide, okay. There were my 7 employees. So this is my standard deviation. The variance is just that number squared. And again, just all you really need to know right now is the bigger the number, the less consistent our data, the more spread out it is. Any questions there? So we have like 3 things left to cover in this section. There's a couple of theorems, empirical rule and Chebyshev's inequality, and then we'll talk about weighted means. So we'll finish that Monday. I'll go ahead and give you the homework and you can start it now, but it won't be due until Tuesday after I finish the section. So we are going to do the entire assignment for the section. Let me kind of look how far you can get right now. You can probably do the first 4 for sure. Yeah, probably just the first 4 right now. And let's do, I want you to do at least 1 standard deviation by hand, and then you can use the calculator for another one. So I would say 14 would be probably the easiest one to do by hand. So 14, let's say you have to do that one by hand. The others you could do hand if you really wanted to, or you could do the calculator.